In this video, we're going to be using period to evaluate trigonometric functions. But in order to do that, we need to talk about what exactly a periodic function is. Now, many cyclical patterns occur in nature, such as the changes of seasons, the rise and fall of the tides, and the phases of the moon. Now, in many cases, we can predict these behaviors by determining the period of one complete cycle. For example, an observer on Earth would note that the moon changes from a new moon to a full moon and back again to a new moon in approximately 29.5 days. Now, if m of t represents the percentage of the moon seen on day t, then m times t plus 29.5 is going to equal our m of t for all t in the domain of m. Now, we say that m is periodic because it repeats at regular intervals. So again, it's periodic because it repeats at regular intervals. So in this example, the period is 29.5 days because this is the shortest time required to complete one full cycle. So the definition of a periodic function is saying that a function f is periodic if your f of t plus p equals f of t for some constant p. So the smallest value p for which f is periodic is what we call the period of f. Now, the period for sine and cosine functions, which are periodic, is 2 pi. And likewise, the reciprocal functions, cosecant and secant, are also periodic with a period of 2 pi. However, the period of tangent and cotangent functions is pi. And we can see that here. So again, sine, cosine, secant, and cosecant all have periods of 2 pi, but tangent and cotangent have periods of pi. And here we see the property listed that allows us to look at that and see that. The first one is in radians, and the second one is in degrees. So let's go ahead and let's do an example. So we're going to use period to evaluate trigonometric functions. So we're going to use the unit circle and the period of the function to evaluate the expression. The first expression is going to be the sine of negative 11 pi over 6. So we're going to use our property from above to help us with this. So here we're going to have the sine of negative 11 pi over 6, and then we're going to add 2 pi to that. And we can see that up here. We're going to add 2 pi to that. That's going to give us our sine of t, or what we're really looking at here. So if I add that together, I now have the sine of, and when I add these together, that's going to give me pi over 6. And then if I look at my unit circle at pi over 6, I'm going to see that I have radical 3 over 2, comma 1/2. And because I'm looking for sine, I want the y value there. So my answer is going to be, 1/2. So we can say that the sine of negative 11 pi over 6 equals 1/2. Now the second one that we're going to look at is the tangent of 225 degrees. So we're going to use this property right here. So the tangent of 225 degrees, and we're using degrees, so we're going to use that 180. But we're not going to add it. We're going to subtract it. Why are we going to subtract it? So the reason we're subtracting it is because if I was to graph 225 degrees, 225 degrees would end up over here. And if we take a look at that, we see that we are actually past the 180 mark instead of in front of it. So we're going to use minusing 180. We're essentially finding our reference angle here. And so that's going to give me the tangent of 45 degrees. And on the unit circle, we have radical 2 over 2, comma radical 2 over 2, and tangent is the y over the x. And so we can go ahead and divide those, and that's going to give us, so if we see radical 2 over 2 divided by radical 2 over 2, those cancel out and give us a 1. So here we have a value of 1. So that's our answer. Let's go ahead and give ourselves a little bit of space. Would be that the tangent of 225 degrees equals 1. So again, kind of what we're doing right here is we're finding the reference angle. That's what we're doing. We're finding our reference angle. Because then we're able to then use our unit circle to evaluate it.